All right, welcome back to another lecture. This is going to be the last section in Unit 3. We're almost done. There's just a few more topics that we'll cover in Unit 4, but we're almost done with everything in this course. And this unit, or this section rather, is just going to be a summary of what we talked about in Chapter 3. There will be one new topic here that we haven't discussed, and that's type 1 and type 2 errors, but they're related to hypothesis testing, and so it shouldn't be too difficult to kind of grasp what's going on there. But there, in this unit, we were focusing on inferential statistics, and there are two main tools that we use to perform inference. One of them is hypothesis testing, and the other is confidence intervals. So what I want to do in this section is take some time to review each of those things. And then while we're reviewing the logic behind hypothesis testing, we'll discuss type 1 and type 2 errors. And that's, like I said, the only kind of new thing in this section. And then once we've done that, I just want to practice setting up some hypothesis tests in a mixed practice kind of way, because it's one thing to be able to run a hypothesis test when you know that every hypothesis test you're running is a one sample proportion test. But what do you do when you're just confronted with a situation and you have to decide which test to apply, right? So that requires a little bit of practice, and that's one of the things that we'll do in this unit. So first, let's talk about the logic behind hypothesis testing, okay? Hypothesis testing is how we judge whether evidence is mathematically compelling. We use it to decide whether the data that have been collected are adequately explained by the null hypothesis, or if those data indicate that we should be rejecting the null hypothesis, okay? So in hypothesis testing, we think of the null as the status quo. It's what we assume to be true until we have evidence otherwise, right? It indicates no change, no difference, no effect, okay? Whereas the alternative hypothesis is usually the statement that we're trying to find evidence to support, and it's going to be a statement that indicates that there is a change or a difference or an effect. Every hypothesis test is going to follow the same steps, right? So step 1, state your hypotheses, okay? And then step 2 is to gather the sample evidence. Now, we can use that sample evidence then to compute a p-value, and what the p-value is it's the probability of obtaining the sample evidence that we obtained in step 2 if we assume that the null hypothesis is true, okay? If the resulting probability is small, okay, then that means that it's highly unlikely that we would have obtained the evidence that we obtained here if we assume the null hypothesis to be true. And so therefore, we should reject the null hypothesis, okay? Because what we observed is what we observed. So if we're getting a small probability, then that indicates that our assumption is probably wrong, so we reject it, okay? How small does the p-value need to be in order for us to reject the null hypothesis? Well, it has to be smaller than alpha, right? So that's step 4 of the process. We use our p-value to make our decision. If the p-value is less than alpha, we reject the null hypothesis. If it's not less than alpha, then we do not reject the null hypothesis. And then finally, step 5 is to write a conclusion, right? Your decision tells you whether or not to reject the null. The conclusion tells you what that decision means for the alternative, okay? So this stuff we've talked about a second ago. P-value is the probability of obtaining our sample evidence if the null hypothesis is assumed to be true. Now, one question that comes up sometimes is, well, hold on a second. Why do we reject the null? Maybe what's actually happening is that we're getting a strange result with our p-value because the sample evidence we collected is strange. Like maybe there was something wrong with our sampling technique, for example. That could be the case, and it's good to scrutinize things like that. However, from a mathematical point of view, like mathematically speaking, when we're computing the p-value, when we're doing that computation, the only assumption we make is that the null hypothesis is true. And so mathematically speaking, if we're getting a small p-value, then that indicates we should reject our assumption. We should reject the null hypothesis, okay? Let's practice interpreting p-values. This is something we've done many times before, but we'll do it again here. So it says, suppose you want to test h null p equals 0.41 against h alternative, right, p less than 0.41. You collect a sample that has a sample proportion of p hat equals 0.38. You run the appropriate hypothesis test and get a p-value of 0.2143. So we're asked to interpret that p-value. Okay, we're asked to give both a mathematical equation and explain it in words. Since we've done these kinds of things before, I would say go ahead and give the video a pause and give that a try. Okay, so your interpretation could say something like this, right? If we assume that the population proportion is p equals 0.41, then there's a 21.43% chance of obtaining a sample whose sample proportion is 0.38 or less. Okay, why or less? Well, because if 0.38 is strange, right, then anything smaller than that would also be strange, right, since 0.38 is less than the null value. So if 0.38 is strange, anything smaller than 0.38 would also be strange. So you could also phrase that in other ways, right? You could say something like, well, there's a 21.43% chance that we would obtain a sample proportion of 0.38 or less if the null hypothesis is true, right? So there are other ways that you could phrase it. Here's what it would look like in math symbols, right? So our p-value is the probability that we would obtain the sample proportion that we obtained, or something more extreme than that, so in this case less than that, given that the null hypothesis is true. Well, what does the null hypothesis say? The null hypothesis says that p equals 0.41. Okay, so this is the probability that we're computing when we compute the p-value. And we're told that it's approximately, or I guess we weren't told it was approximately, we were told it's exactly 0.2143. So that's how we would write it down in math symbols. Okay, part B. Suppose you want to test H null mu equals 75 against H1 mu greater than 75. You collect a sample that has a sample mean of X bar equals 78. You run the appropriate hypothesis test and get a p-value of 0.0143. We're asked to interpret this p-value. So go ahead and give the video a pause and write down your interpretation. Okay, so the interpretation here would be, if we assume that the population mean is mu equals 75, then there is a 1.43% chance, okay, a 1.43% chance of obtaining a sample mean of 78 or more. Now this time I'm saying or more because 78 is more than our null value of 75. So if 78 is unusual, then anything more than that would also be unusual. To write this down in math symbols, we would say this. Our p-value is the probability of obtaining the sample mean that we obtained, okay, 78, or more, okay, so greater than or equal to 78, given that the null hypothesis is true. Well, what does the null hypothesis say? In this case, the null hypothesis says mu equals 75. So this is the p-value, and we're told that this is equal to 0.0143. Okay, so that's the p-value. Now, exactly how small should the p-value be in order for us to reject the null? Well, as we've said, it needs to be smaller than alpha, smaller than our level of significance. Alpha is the probability of committing a type 1 error, and that's why we need to talk about type 1 and type 2 errors in this section so that you understand what that means, okay? But I'll just tell you right now, a type 1 error is when you reject a true null hypothesis. Okay, so alpha is the probability of rejecting a true null hypothesis. Now, alpha is chosen by the researcher. So we, in this class, we've never had to choose the level of significance. It's always been given to us. But the way that the researcher would make that decision of what level of significance to set is based on the severity of making a type 1 error. Okay. Now, one of the things that we've discussed with alpha is that alpha is the complement of our confidence level. Okay, so if we have a 95% level of confidence for a confidence interval, for example, then alpha would be 0.05 because 100% minus 95% is 5%, and 5% is the same thing as 0.05. What that means is if we want to be 95% confident that we're not rejecting a true null hypothesis, then the p-value needs to be less than 0.05. If we want to be 99% confident, then the p-value needs to be less than 0.01. If we're okay with just being 90% confident, then p just needs to be less than 0.10. Okay, and in general, if we want to be this confident, then the p-value needs to be less than alpha. Now, when it comes to our decision is always about the null hypothesis. We're always deciding either to reject or to not reject the null. We're never making any decisions about the alternative. Okay, the decision is always about the null, and we never accept the null. When we decide not to reject the null hypothesis, that is not the same thing as accepting the null hypothesis. It's kind of similar to a criminal trial, right? A not guilty verdict is not the same as declaring someone innocent, right? Sometimes there's just not enough evidence to convict the defendant, even though the defendant might be guilty, right? And so consequently, it's the same way with hypothesis testing. We're not accepting the null hypothesis when we fail to reject it. So we just say, do not reject the null in our decision. And then finally, one last thing that I've harped on over and over and over again is that when we're making our decision and conclusion, all of the positive statements go together and all of the negative statements go together. Okay, so if the p-value is less than alpha, then we reject the null and there is sufficient evidence to support the alternative. If the p-value is not less than alpha, then we do not reject the null and there's not sufficient evidence to support the alternative. There is never any mixing and matching in hypothesis testing, okay? All of the positive statements always go together and all of the negative statements always go together. So with that, now let's talk about type 1 and type 2 errors, okay? When we're running hypothesis testing, the reason that we're doing that is because we're trying to figure out what reality actually is. But we'll never fully know what reality actually is, right? And not only that, but our hypothesis test is based on sample information, so it's based on incomplete information. So we can never be 100% certain that the conclusions we're arriving at are the correct conclusions to arrive at. In fact, there are 4 possible outcomes. So there's some kind of reality that we don't know, but we're trying to run a test to figure it out. And then based on the results of our test, we'll come to some kind of conclusion. If the conclusion that we arrive at matches with reality, then we've made a correct decision, okay? So if we have a true null hypothesis and we decide not to reject it, then we've made a correct decision. If we have a false null hypothesis and we decide to reject it, then that's also a correct decision. But there could also be mistakes, right? We could also make an error. Okay, we could decide, for example, to reject a null hypothesis even though the null hypothesis is true, and that would be called a type 1 error. This is sometimes called a false positive. Okay, and then on the other hand, we might decide to not reject the null hypothesis even though the alternative hypothesis is true. That would be bad as well, because if the alternative is true, we want to reject the null. So if we decide not to, then we've committed a type 2 error. This is sometimes called a false negative. That's the worst N I've ever seen. A false negative. Okay. So for example, if you know for a fact somehow that you don't have COVID, but you take a COVID test and it comes back positive, then that's a type 1 error, right? It's a false positive. On the other hand, if you somehow know for sure that you do have COVID, but you take a COVID test and it comes back negative, then that's a type 2 error. It's a false negative, right? So thinking of this like a criminal trial, a type 1 error would be like convicting an innocent defendant. In other words, it would be sending an innocent person to jail, right? That's a type 1 error. A type 2 error would be like acquitting a guilty defendant. In other words, it would be like letting someone go free when they're guilty. These things happen, right, in criminal trials. And that's because we never fully know what the reality is. We just based our conclusions on as good of evidence as we can get and kind of go from there. But it is possible that sometimes you're convicting an innocent defendant, right? In other words, committing a type 1 error. And sometimes you're letting a guilty defendant go free, committing a type 2 error. We hope that those errors are kept to a minimum. And they are if we're using correct, procedures. Anyway, let's look at some examples and talk about what it would mean to make a type 1 and type 2 error. This one says a drug company is trying to develop a new antibiotic, but the FDA will not approve it if it causes headaches in more than 2% of the population. The researchers run the appropriate hypothesis test to determine if their drug causes headaches in more than 2% of the population. Okay. Explain what it would mean to make a type 1 error in this case. Well, again, a type 1 error is a false positive. It's rejecting a true null hypothesis. So to commit a type 1 error in this case would mean to conclude that more than 2% of people experience headaches as a result of this antibiotic, when in reality, only 2% of them do. Okay, so a type 1 error would mean concluding that more than 2% of the population experience headaches as a side effect, when in reality, only 2% of them do. Okay, what would it mean to make a type 2 error? Well, it would be just the opposite, right? To commit a type 2 error would mean that that we conclude that only 2% of people experience headaches as a side effect, when in reality more than 2% of them do. Okay, so that's type 1 and type 2 errors. As stated previously, the probability of making a type 1 error is called the level of significance, and we have a special letter for it, right? We call that alpha. And as we commented on earlier, alpha is chosen based on the severity of the consequences of making a type 1 error. We won't have to choose any alphas ourselves in this course. Alpha is given to us, but that's how the researcher would decide. Now, you might think, why don't we just make alpha as small as possible? And the answer to that question is because reducing the probability of making a type 1 error increases the probability of making a type 2 error. So it's somewhat of a balancing act. As we've seen, the most commonly used values are 0.01, 0.05, and 0.10, but of those three, 0.05 is kind of the standard value that's used for a type 1 error. Okay, so that'll do it for the logic behind hypothesis testing. Let's talk about the logic behind confidence intervals, okay? Hypothesis tests help us to determine if there's a difference, right? Hypothesis tests tell us whether the sample evidence we're seeing indicates that there's a deviation from the null value, okay? But they don't tell us anything about the magnitude of that deviation. They don't tell us how much of a difference there is. Okay, so hypothesis tests tell us if there's a difference, but they don't tell us how large the difference is. If we want to get a handle on how large the difference is, then using a confidence interval is helpful, right? Because what confidence intervals do is they give us an estimate of our population parameter. So they can give us some indication of how big of a difference there might be. So hypothesis tests tell us information about statistical significance. They answer the question, is there a difference? Confidence intervals, on the other hand, give us information about practical significance. They answer the question, how big is the difference? Okay? Now, because our estimates are based on sample information, okay, incomplete information, we are 0% sure that our parameter is equal to the sample statistic that we used to estimate it. If we want to have any level of confidence in our estimate whatsoever, we have to give a range of values that the parameter could equal, and that range of values is called a confidence interval. Okay? We've seen many of these. Let's practice interpreting some. So number 3 here says, interpret the following confidence intervals. Part A, a 95% confidence interval for the proportion of drunk drivers on the road between 1 and 2 p.m. is 0.034 to 0.042. I'll let you pause the video and write down an interpretation of that. Okay. Okay, so your confidence or your interpretation could say something like this. We're 95% confident that somewhere between 3.4% and 4.2% of drivers on the road at this time are drunk. This time, right, are drunk. So from 1 to 2 p.m. You could say that differently. You could say something like, we're 95% confident that the proportion of drunk drivers from 1 to 2 p.m. is somewhere between 3.4% and 4.2%. Or you could say, we're 95% confident that the proportion of drunk drivers on the road between 1 and 2 p.m. is somewhere between 0.034 and 0.042, right? So there are a whole bunch of different ways that you could say it, but that's the idea. Part B, a 90% confidence interval for the mean age in years of drunk drivers on the road between 1 and 2 p.m. is 21.3 to 24.2. So once again, I'll let you give the video a pause and write down an interpretation. Okay, so your confidence or your interpretation here could say something like we're 90% confident that drunk drivers on the road at this time are between 21.3 years old and 24.2 years old on average. Okay, there are other ways that you could say that. You could say we're 90% confident that the true population mean age of drunk drivers on the road between 1 and 2 p.m. is somewhere between 21.3 and 24.2 years old, right? So there are other ways that you could phrase this, but that's the idea for part B. Let's look at a couple more. I think part C and D are for 2 sample tests. So let's take a look. Part C says a recent survey found that 67% of U.S. women and 65% of U.S. men plan to vote in the next presidential election. A 99% confidence interval for the difference in the proportion of women and men who plan to vote is 0.011 to 0.029. Okay, so go ahead and give the video a pause. See if you can write down an interpretation. Okay, so here's one interpretation, right? You might say something like, we're 99% confident that women are somewhere between 1.1% and 2.9% more likely to vote than men. Another acceptable interpretation would be to say, we are 99% confident that the true difference in the proportion of men and women who will vote is somewhere between 1.1% and 2.9%. Okay, so something along these lines. Okay. Part D, a recent survey found that the mean height of registered Democrats is 55.2 inches and the mean height of registered Republicans is 57.4 inches. A 95% confidence interval for the difference in the mean height in inches of Democrats and Republicans is negative 2.8 to negative 1.6. Once again, give the video a pause and write down an interpretation. So here's one possible interpretation. You could say something like, we are 95% confident that Democrats are somewhere between 1.6 inches and 2.8 inches shorter than Republicans on average. That one might seem a little bit tricky because I'm reversing the order of the confidence interval here, but that's because I'm talking about them being shorter. I could change the perspective and say something like, we're 95% confident that Republicans are somewhere between 1.6 inches and 2.8 inches taller than Democrats on average. Or I could say something like, we're 95% confident that the true population mean difference in height between Democrats and Republicans is somewhere between negative 2.8 inches and negative 1.6 inches, right? So, something like this. So all of those would be appropriate interpretations. Okay, so that's how confidence intervals work. Let's do some mixed practice now. What I want to do is just practice setting up a whole bunch of different hypothesis tests. And so just to refresh our memory on the hypothesis tests that we've talked about, here's a list. So far, we've talked about 8 hypothesis tests in this class. In Unit 4, we'll introduce one more hypothesis test. Okay, but these are the 8 that we've talked about so far. We had 4 tests for proportions. Okay, the 1 sample proportion test, the 2 sample proportion test, the goodness of fit, and the homogeneity of proportions test. We also had 4 tests for means. We had the 1 sample T, the 2 sample T, the matched pairs T, and the one-way ANOVA. When you are confronted with some scenario where you're asked to run a hypothesis test and you have to decide which of those 8 tests to apply, I think that the first thing you should do is ask yourself what parameter you're testing. What parameter? Am I looking at proportions or means? Because then you're narrowing it down quite a bit. If you know that you're testing proportions, then you know that you're in one of these 4 scenarios. If you know that you're testing means, then you know that you're in one of these 4 scenarios, right? So being able to determine what parameter you're testing narrows it down quite a bit, right? Now, how do you do that, right? How do you determine which parameter, proportions or means, you should be testing? Well, sometimes the problem will just come out and say so, right? If the problem says something about means or averages, then you're most likely testing mu, right? If the problem says something about proportions or percentages, then you're most likely testing p. If the problem doesn't use those keywords, then you should ask yourself, what kind of variable are you testing? What kind of variable are you looking at? If the variable is categorical, then you're most likely testing proportions. If it's numerical, then you're most likely testing means. Okay, once you've decided what parameter you're testing, then the next question to ask yourself is, how many parameters am I testing, right? So if you know that you're testing proportions, for example, then you should next ask, how many proportions am I testing? If the answer is 1, well, then you'll run a 1-sample proportion test. If the answer is 2, well, then you'll run a 2-sample proportion test, okay? If the answer is more than 2, right, if you're testing more than 2 proportions, then you have to decide whether you're going to use the goodness of fit or the homogeneity test. And probably the best way to do that is to ask yourself if you have exact values for each proportion in the null hypothesis. Okay, so if you have a scenario where you're going to be testing P1 equals 0.7 versus P2 equals 0.35, etc., then that's a goodness of fit test. If you don't have those exact values for the null hypothesis, if the thing that you're going to be testing is P1 equals P2 equals P3, right, then that would be a homogeneity test, okay? Similarly for the means, okay? If you know that you're going to be testing means, well, then you should ask yourself, how many means am I testing? And if it's just 1, then you'll run a 1-sample T. If it's 2 means, then you'll have to ask yourself, okay, are the samples independent or dependent? If they're independent, you run a 2-sample T. If they're dependent, then you run a matched pairs T. And then finally, if you're testing more than 2 means, you run an ANOVA. Okay, so this is how we decide which test to apply. That will require some practice, okay? And that's what this section is for. That's also what the practice test is for. Strongly encourage you to do practice test 3 before test 3, because you need practice. You need practice figuring out which test to apply in which situations. Let's just look through a few examples. And here, I don't want to actually run the test. I just want to set up the test, okay? If we can set up the test and figure out which app to use, then the rest is history, right? So here we go. It says, in October 1945, the Gallup organization asked 1,487 randomly sampled Americans, do you think we can develop a way to protect ourselves from atomic bombs in case other countries tried to use them against us? 788 responded, yes. Did a majority of Americans feel the U.S. could develop a way to protect itself from atomic bombs in 1945? Go ahead and give the video a pause. See if you can write down the hypotheses and the app that you would use to get the p-value. Okay, here's my solution. This one is going to require a little bit of explanation, I think. Notice that this problem didn't say anything about proportions. So how do I know that I'm testing a proportion? Well, because if you think about what the raw data would have looked like, the researcher went out and they asked people, do you think we can develop a way to protect ourselves from atomic bombs? And then people either said yes or no, okay? So the raw data would have been a list of yeses and nos. Well, you can't compute the mean of a list of yeses and nos, right? That's a categorical variable. So we must be testing the proportion here, right? This is how I know that we're testing the proportion. I know that we're only testing one proportion in this case because we only have one group of individuals, right? The organization asked this number of individuals. It's just one sample, so I should be running a 1-sample proportion test. Now, in running the 1-sample proportion test, I need to know what the null value is, and I need to know what the alternative hypothesis is. So let's talk about that. I know that what I'm being asked to do is figure out if a majority of Americans felt we could develop a way to protect ourselves. Well, majority means more than 50%, right? So the null hypothesis is going to say, no, it's not a majority, it's just equal to 50%. Whereas the alternative is going to be, yes, a majority, right? More than 50%. Okay, and so that's how I got the 0.5, and that's also how I got the greater than sign, because that's what we want to test. We want to know if more than 50% of people felt we could develop a way to protect ourselves. The app that we would use to run this test would be Inference for a Proportion. Okay, so that's the app we would use in Art of Stat. Okay, part B. Among individuals who had credit cards in 2010, the mean number of credit cards was 3.5, according to the Federal Reserve Bank of Boston. A random sample of 160 credit card holders has a mean of 3.3 cards and a standard deviation of 2.3 cards. Do these results imply that the mean number of cards per individual is now less than 3.5? So go ahead and give the video a pause, see if you can write down the hypotheses and the app that you should run. Okay, these are the hypotheses that you should have here. Okay, I know that I'm testing a mean because in this case the problem came out and just directly said it. Okay, do these results imply that the mean is such and such? So the null hypothesis is going to be that mu. Oh, and by the way, I know that I'm only comparing one mean because I only have one sample, right? It was one sample of 160 credit card holders. So it's a one sample mean test, a one sample t-test. Okay, so the null hypothesis is going to be that mu equals something. What should the something be? Well, the status quo is that the mean number of credit cards was 3.5. Okay, and we're trying to test to see if the number of credit cards is now less than 3.5. So the null hypothesis is going to be, no, it's not less than 3.5, it's equal to 3.5. It's the same as it was before, okay? And the alternative is the thing that we're trying to test, right? Yes, it's less than 3.5. Because we're running a one sample t-test, the app that we would use is Inference for a mean. Okay, part C. Kumon promotes a method of studying mathematics that it claims develops mathematical ability. In one question on an exam, a random sample of 350 non-Kumon students resulted in 73 getting the correct answer. For the same question, a random sample of 400 Kumon students resulted in 130 getting the correct answer. Are Kumon's claims substantiated? Give the video a pause and write down what hypothesis test you would use here and what app you would use to get the p-value. Okay, these are the hypotheses you should have. We're testing proportions here. Again, the raw data would have been a list of yeses and nos. Basically, right? The researchers would have said, did the student get the question correct? Right? Yes or no. And so it would have been a list of yeses and nos. And what we want to count up is the number of successes, right? The number of times that they got the correct answer. So we'll compare the percentage of times that they got the correct answer. Now, I know we're comparing two groups because the problem clearly indicates that we're comparing two groups, right? We had a random sample of 350 non-Kumon students, which I'm calling group 1, and then another random sample of 400 Kumon students, which I'm calling group 2. So since we're comparing two proportions, the null hypothesis is going to be that P1 equals P2. As for the alternative, we want to know if Kumon's claims are substantiated. Well, what are Kumon's claims? They claim that they have a method of studying mathematics that develops mathematical ability. Well, if that's true, then we would expect the Kumon students to get the question right more often. In other words, we would expect the proportion of Kumon students who got the right answer to be greater than the proportion of non-Kumon students who got the right answer. So we would expect P2 to be bigger than P1. Or in other words, that means P1 would have to be less than P2. And that's how we ended up with the left-tailed test. We're comparing two proportions, and so that's the app that we're going to use in Art of Stat, right? Compare two proportions. Part D. The following data represent the daily volume in millions of General Electric stock and Pfizer stock on the same 13 randomly selected days in 2010. Determine if the daily volume of GE stock is greater than that of Pfizer. Once again, give the video a pause. See if you can write down the hypotheses and the app that you would use to get the p-value. Okay, these are the hypotheses you should have here. In this case, the problem did not say anything about means or averages. Okay, so we just have to kind of intuit this. The benefit here is that we were given the raw data. And so we can just look at the raw data and we can tell the data are numerical. So when you have numerical data, you're going to be comparing means. And that makes sense. When we're asked to determine if the daily volume of GE stock is greater than that of Pfizer. Well, is the daily volume greater in GE? Sometimes it is, okay? Sometimes it isn't. So when we say, is the daily volume of GE stock greater than that of Pfizer, it's clearly implied that what we mean is on average, right? Is the daily volume of GE stock on average greater than the stock of Pfizer, than Pfizer's stock, right? So we're comparing means, averages. Now, we know that we're comparing two groups because we're supposed to be comparing GE to Pfizer, okay? Two groups there, clearly. And we know that it must be a right-tailed test because the problem says so, right? It says if we call GE group 1 and Pfizer group 2, then we want to know if group 1 is greater than group 2. Okay, so mu1 greater than mu2. We're comparing two means, so we'll use the compare two means app. But now here's a trick, or here's something that's a little tricky. When you're comparing two means, you have to decide if the samples are independent or dependent. And in this case, the samples are dependent, okay? Because we have matched pairs. The reason I know that is because the daily volume, these numbers in this chart are the daily volume of GE and Pfizer stock on the same 13 days. In other words, once we chose the GE stock for, let's just say that this day was February 3rd or something, right? Then we automatically got the Pfizer stock for that same day, right? They're matched pairs. These are the same day, right? So this is February 3rd, let's say, and maybe this one is March 15th, and maybe this one is March 17th, and so forth, right? But they're clearly matched pairs, right? Dependent samples. Okay, part E. In the Space Lab Life Sciences 2 payload, 14 male rats were sent to space. Upon their return, the red blood cell mass of the rats was determined. A control group of 14 male rats was held under the same conditions except for spaceflight, and their red blood cell mass was also determined. The project resulted in the data listed below. Does the evidence suggest that the flight animals have a different red blood cell mass from the control animals? Give it a pause. See if you can come up with the correct hypotheses. These are the hypotheses that you should have. Once again, the problem doesn't say anything about means or averages, but clearly looking at the data, I've got numerical data, so chances are I'm comparing means. Okay, I could also think of it like this. Does the evidence suggest that the flight animals have a different red blood cell mass? Well, sure, like some of the flight animals, this flight animal has a different red blood cell mass from that control animal, right? So like obviously on a case-by-case basis, but that's not really the question, right? It's implied that what we're asking is on average, right? On average, do the flight animals have a different red blood cell mass than the control animals, right? Do the flight animals as a group, on average, have a different red blood cell mass than the control animals as a group, on average? So we would be comparing means here. Clearly, there are two groups that we're comparing, so we're going to use the Compare Two Means app. And by the way, we're asked if they have a different red blood cell mass. We're not asked if the red blood cell mass of the flight animals is less than the control animals or greater than the control animals. We just want to know if it's different, and that's why I chose a two-tailed test for this one. Anyway, but yes, we're comparing two means, so we use the Compare Two Means app in Art of Stat. And when we do that, we have to decide if the samples are independent or dependent. In this case, I'm saying that the samples are independent because I don't think we have any matched pairs. It's not like this rat is a matched pair with this rat. If it were, the problem would have had to say something like that. It would have had to say like, we chose a rat and then we chose the rat's sibling from the same litter or something and kept it, in the control group. But it doesn't say anything like that. It just says they chose 13 rats here. And then independently of that, they chose 13 rats there. So that makes this independent sampling. Okay, I think we have three more. So let's look at this next one. The data in the table represent the number of corn plants in randomly sampled rows for various types of plot. Test whether the mean number of plants for each plot type are different. So go ahead and give it a pause and see if you can write down the correct hypotheses in the test or the app to use. Okay, these are the hypotheses that you should have for this one. We were told to test the mean, so right away we know we're testing means. Now, how many means are we testing? Well, it looks like we've got three groups, right? Sludge plot, spring disk, and no-till. So the null hypothesis is going to be mu1 equals mu2 equals mu3. And the alternative is that at least one of those is different from the others. When you're testing more than two means, you run an ANOVA. And that's what the app is called in Art of Stat. So the app that we use is the ANOVA one-way app. Okay. Part G. It is a well-known fact that 24% of children like unicorn giggles very much, 15% of children like them somewhat, and 61% of children like them not at all. A researcher wanted to know if that distribution has changed in recent years. So she conducted a survey asking children, how much do you like unicorn giggles? Very much, somewhat, or not at all? And her results are summarized in the table. Have children's opinions about unicorn giggles changed? I'll let you pause the video, see if you can write down the appropriate hypotheses and the test that you should, or the app that you should use to get the p-value. Okay, here are the hypotheses that you should have. So this might be a little bit confusing to you because you might look at this chart right here and you might see all of these numbers. And then that might make you think that, oh, well, this is a numerical variable, so I should be testing means. But not so, okay? Because this chart is not the raw data, okay? These are not raw data. This chart is a summary of the data, okay? If you think about what the raw data would have looked like, it would have been a list of responses that said very much, somewhat, or not at all, right? It would have been a column of responses that said very much, very much, not at all, very much, somewhat, not at all, very much, right? It would have been this list of responses that's clearly categorical variable. So we're testing proportions here. We want to know what proportion of children fall in each of these three categories, okay? Very much, somewhat, or not at all. So I know I'm testing proportions. I know I'm testing three proportions. And so then the question is, should I be running a goodness of fit test or a homogeneity test? Well, if I were running a homogeneity test, then I would have to be testing to see if the proportions were all equal. But that's not what I'm being asked to test. I'm asked to test if children's opinions have changed. So what I'm actually being asked to test is if children's opinions are still that 24% of them will say very much, 15% of them will say somewhat, and 61% will say not at all. Okay, so I have exact values for P1, P2, and P3. I'm not just testing is P1 equal to P2 equal to P3. I'm testing if P1 equals 0.24, if P2 equals 0.15, and if P3 equals 0.61. And that makes this a goodness of fit test. That's what it's called in Art of Stat, right? It's called a chi-square test. But then remember, when you go to the chi-square test, you have to choose a homogeneity test or a goodness of fit. And in this case, we want a goodness of fit. Okay, last one. A survey was conducted asking children, do you like unicorn giggles? Their responses are summarized in the table below. And it looks like in this table, we've got their ages here, and then whether they like unicorn giggles here. Does the sample evidence indicate a difference in the proportion of children in each age group who like unicorn giggles? So once again, I'll let you pause the video, write down your hypotheses, and the app that you would use in Art of Stat to get the p-value. Okay, so here are the hypothesis tests that, here are the hypotheses that you should have here. Once again, you look at the chart and you might think to yourself, well, I see a bunch of numbers. Clearly, this is numerical data, right? So I must be testing means, but that's not the case, right? Because again, this chart is not raw data. It's a summary of the data. It's already summarizing like how many of the 3 to 4 year olds like unicorn giggles and how many of the 7 to 8 year olds didn't like unicorn giggles, right? So it's not raw data. The raw data would have been a list of yeses and nos. Like it would have been, actually the raw data would have been 4 columns. It would have been like, there would have been a column for the 3 to 4 year olds, a column for the 5 to 6 year olds, and so forth. And then each of those columns would have been yes, no, no, yes, right? No, 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 yes, right? So this is what the raw data would have looked like. And it would have been categorical, right? Clearly categorical. So we're testing proportions. Now, how many proportions are we testing? Well, it looks like we've got 4 categories, right? 3 to 4 year olds, 5 to 6 year olds, 7 to 8 year olds, and 9 to 10 year olds. So 4 categories, that means we're testing 4 proportions. So right off the bat, I know that I'm going to be running a chi-squared test, either a goodness of fit or a homogeneity. Now, how do I test which, or how do I know which one to use? Well, the question asks me, does the sample evidence indicate a difference in the proportion of children? So it's asking me, are the categories different, or are they all the same? Okay. So I'm not given any distribution to test. I'm not given like numbers to say P1 equals 17% and P2 equals 23%, right? I'm not given any of that. I'm just being asked, are the proportions different, or are they perhaps all the same? Okay. And so that's why we've chosen a homogeneity test here. So again, we're going to use the same app as the goodness of fit, but this time instead of choosing goodness of fit, of course, we're going to choose homogeneity as the test to run. So that's the app that we would use. And that brings us to the end of this section and the end of this little mixed practice stuff. Once again, I strongly encourage you to take practice test 3 before you take the real thing, because you'll have an opportunity to do more of this mixed practice, and you'll also have the opportunity to actually run the tests. Okay, so it'll be very helpful for you to practice, doing this sort of mixed practice and thinking through what kind of test to run. But that will do it for this section and this entire unit. We'll have a couple more things to say in Unit 4, but for now, have a good one.